All right, everyone, welcome back. Today is Wednesday, and I'm wearing the same shirt I wore on Monday. Now you're wondering why, because what I just told you, I'm actually filming these back to back. So today is day 2 of our discussion on angular momentum addition, with the end goal of being able to describe term symbols. Term symbols are used for atomic configuration, which are not something that probably you're going to be doing for research. However, the idea of term symbols are that they uniquely describe the electronic configuration, and they do that by addition of angular momentum, which every state is going to be different. We're also going to try to represent this in a way that also tells you the energy. You're going to be doing nitrogen on your exam, and you're going to have 3 states, and one of them is lower in energy than the other. So that's one of the end goals of this. Okay, now who cares about atoms? Nitrogen atoms? You don't find nitrogen atoms in nature, you find N2. Okay, but the term symbols for molecules, which now you do care about, those borrow a lot of the lessons of atoms. They use similar symbols. Linear molecules will instead of an S term symbol, they use a sigma term symbol. And again, to represent spherical symmetry. Right, so when you go to molecules, you're not representing angular momentum so much as you're representing symmetry. But note that S orbitals, S angular momentum is highly symmetric, and P not so much, and less so D. In fact, these have well-defined symmetry elements, right? So when you go to molecules, again, the thing you should care about, you can actually apply all the lessons we're covering here to understand how to read the term symbols, which again tell you the electronic configuration of the molecule. Although we're not going to get that far. It's enough to figure out how to do it for nitrogen, right, on your exam. You're going to do nitrogen. And if you can do that, which you can, you will, you'll be okay. All right. Now to do that, remember that what we're doing is we're going to couple, let me do it the way the book does. Okay, so this is where it's going to start getting confusing. The source of confusion here is that you have to, as we add angular momentum, there's multiple sources of angular momentum. We have S and L. But then when we add more than one electron, now we've got 2 L's and 2 S's, right? You actually have to add them in a certain order, right? So when we're going to add 2 angular momentum things together, you get to decide what those are. Now, as I mentioned, 2 electrons, there's 4 things you know. You know 2 L's, L1 and L2, you know S1 and S2, and their corresponding LZs and SZs. You know all that. But you can only add 2 things at once. So you have to add them in a certain order, and then when you've finished adding these together, you should be at the term symbol, and you can know the energy from that term symbol. So this is where this is going to get a little difficult. This is why your book uses the following terminology. It calls it J, M sub J, and what is often left out is that there's a J1 and J2. Now I want to point out that J1 and J2 can be either like the spin angular momentum of 2 electrons, or it could be like the angular momentum L of a P electron, and J2 could be its S. So you can imagine like what we're going to start out with is that this is S1, S2. So I'm going to describe adding the angular momentum, the spin angular momentum of 2 electrons. Or I could add, for a single electron, it's L and it's S. So J1 and J2 can represent anything. Now your book says that, but I think it's kind of confusing. Of course, J and M sub J are the resultant, what happens when we add them together. Okay, now remember I said, there's going to be some operation, and we're going to start learning how to do that operation. What we know this. We know the spin of 1 electron is SZ. Okay, so in electrons, the spin S, is always 1/2. Right, electrons are their intrinsic spin, their intrinsic S is always 1/2. SZ1 can be plus half or minus half, right? Alpha, beta, up, down, plus, minus. Okay, now I've got the same for a second electron. I've got 2 electrons. Okay, so, and now let me make this more real. Let's talk about a 1s1, 2s1 state of hydrogen. So it's an H minus. Now what does that look like? And we won't have any P's. We're not going to include any P's because those have L angular momentum. Let's not confuse ourselves. So we're going to do this. So how do we do that? Again, we have to add those angular momentums because, I mean, see, here's the thing that's frustrating, right? It's like you're looking at this and thinking, well, what else could I possibly know? I obviously know everything I need to know from this. And the answer is maybe, maybe not, right? Because, okay, so I can, and honestly, I can tell that that's a triplet. I can tell that's a triplet, right? And you can tell that that's a triplet. Spin down, spin down. Okay, but now, again, to motivate you, what about this one? Spin up, spin down. Or, I'm sorry, spin down, spin up. Or what about spin up, spin down? You might recall that those are neither singlet, or triplet, but linear combinations are. So this is what we're getting to. Anyway, we're going to do this, but my point to you is that you really can't look at these drawings and really know anything. Not yet. So we're going to diagonalize this in a sum basis. Okay, now how are you going to do that? Okay, first let's remind ourselves what, again, this question mark means what's the operation to go from one to the other. In this case, we're going to diagonalize a matrix. Okay, I want to remind you, and I'm going to, S1 and S2 are half. I don't need to write that. I need to say plus half, minus half, plus half, minus half. So I'm going to reduce this. I'm going to call that M1, M2. I don't want to write S over and over again, S1 and S2, when it's just always a half. Okay. S1 squared will, of course, be H bar squared, S1 times S1 plus 1. Of course, notice that this is that in this basis, this S1 SZ1 basis, that these are eigenstates of S1 squared. So same for S2. Obviously, S1 and S2 are not S1, S2. Okay, then we can do S1Z on M1, M2. And of course, we get H bar M1, M1, M2. And then the same for S2Z. Okay, so again, the ground rules are simple. Okay, now the J in this case is going to be the total spin, the summed spin angular momentum for 2 electrons. And again, I made it easy because they're both in S states. We don't have to worry about that. There's no reason to worry about L at all. So I didn't have to do that, I just want to make it a little easier. Okay. Now, I covered this last time, but I got how to write these operators. So S, I'm going to do it again. Remember last 5 minutes ago when I wrote the operator out all the way? I'm going to do that again. So heads up. Okay. Total spin is S1 plus S2. Okay, that's no-brainer, right? Okay. So therefore, okay, you're going to hate this. S squared. So remember, I was saying the other day, you got to be careful about assuming like, oh, if I know what S is, and S squared is just doing the same thing twice. There shouldn't be any issues. There are issues. There are major issues. And so I'll show you that. Okay. S squared is S1 squared plus S2 squared. Okay, that's brainless. But where you got yourself a bit of a problem is that you got 2S1 dot S2. And that's the source of coupling, and that's why we have this giant problem of knowing this, but it's not actually useful. And I'll explain a little bit more about, I think I've said a bunch, but I'll explain a little bit more again why it's not useful. I'll do that at the end. All right. So anyway. Okay, so what is S1 dot S2? I bet that's not clear. So what you do is so it actually is really not too bad. You get S1x, S2x, plus S1y, S2y. So you kind of, you probably could have guessed this one, right? S1z, S2z. Okay. And then, let's see here. Sorry, I'm blanking out. Okay, so now recall that we have our plus and minus operators, right? So that's why I spent a lot of time on that on Monday. I don't think you need to review them. Just trust. You know that S plus and S minus, the raising and lowering spin operators, are related to Sx and Sy. Right? We covered that last time. So I wouldn't try to wade through the algebra. Just trust me when I tell you that it's this. S1z, S2z. Remember that S plus and S minus are x and y deals. Okay, so what you end up with is plus 1/2 S1 plus S2 minus plus S1 minus S2 plus. Remember, these are raising and lowering operators. Okay. So, now these, they get little hats. They need hats. Okay. Now let me go further. Okay. I'm not using the boards today. So S squared is now S1 squared. Remember that was just the dot product of S1 and S2. So we still have S1 and S2 plus 2 S1z, S2z, plus S1 plus S2 minus plus S1 minus S2 plus. Everyone gets a hat. What a happy day. There we go. Oh, hat. There we go. Okay. And of course, remember that takes M1, and it makes it M1 minus 1. And of course, if M1 is already beta, or the minus state, then S1 minus makes everything 0. Because you can't lower, you don't have a spin less than minus 1/2. There's no gamma spin or anything like that. Okay, so God, why did I write all that? Okay, so the point of this is S squared and S actually commute. Remember, you can't take that for granted. S2, sorry, what am I doing? Let's say S1, right? There's no just S. S squared and S1, S2 commute, and let's look at that. Why would we commute, right? So one of the reasons you got to get rid of the z's is because of that. I'm sorry, x's and y's. Anyway. Okay, and then what else have I got? Okay, now here's the problem. S1z and S squared, sorry I didn't do this in order, is not 0, and S2z and S squared is not 0. Okay, so again, the big picture there is that this picture of, this picture of up, down, up, down, you're going to lose that. You're not going to be able to identify necessarily what electron is pointing in what direction. You cannot identify whether if this is the first electron, you're not going to be able to identify whether it's up or down, and ditto for this one. Once you do this transformation, the transformation is, however, necessary. Now, it's great that I can draw this quite easily. We learned this as freshmen, but it doesn't tell you s squared, because s squared doesn't commute with it. If you don't know s squared, you don't know anything. And what I'll tell you is you don't know the energy. You don't know the energy of the atom unless you know s squared. That means that this information is actually useless. It's not useless, it's a starting point, but it has to be transformed. All right, now anyway, now of course the way we're going to do this is we're going to, I'm going to use some shorthand. We're going to diagonalize the s squared matrix in the S1, S1Z, S2, S2Z, what I drew here in that basis. All right, and then we'll have the eigenstates of s squared, and then we'll know the energy. And I'll explain a little bit more on that, what the energies are. Anyway, okay, now what I'm going to do though is I'm going to call this remember S1 and S2, because these are intrinsic spins, the spins we don't really know what they are, it's always a half. So I don't want to write S1 and S2 a bunch of times. I'm just going to write M sub S1, M sub S2. So I'm going to do that plus plus, minus minus, plus minus, and minus plus. So those are the four states, and I will make the s squared matrix using those basis states. Okay, now just so your mind isn't totally blown, you can work through this yourself if you feel like. This takes a while. All right, here's your Hamiltonian. Now you know what plus plus does. Yeah, you should know this at this point. I've written all these out. It oddly does take a while to do this. And I was going to work through it all, but screw that. That sucks. Okay, so what do you get? Okay, now hold on. Just to show you, you know what this is. 3/4 h bar squared, right? The total spin, we've covered s squared. It's just for the first electron. So that's 3/4, right? Okay, and then the same for the second electron. It's automatically 3/4 h bar squared. Okay, now where it gets a little tricky is okay. Now we're here, right? No, sorry, we did this and this one, this one. Okay, now what about this one? This is going to be, these are plus plus. So this is going to be h bar squared over 4 times 2. So this is h bar squared over 2. This one right here. So remember, since this is plus plus, this is h bar over 2, h bar over 2 times 2. So that's h bar squared over 4. So, right, this isn't turning out to be too horrible. Okay. This one takes plus plus and it turns it to plus minus. This one drives it to 0 because raising plus isn't possible. So again, plus plus. This guy, plus minus, this guy kills it because you can't raise the first plus further. There's no double plus. Okay. Plus plus, killed it. Can't raise the, plus plus, the second plus can't be raised. So these are dead. And by the way, this is 2h bar plus plus. Am I using the wrong? No, I'm using the right orders. Okay. Now, let me do s squared. Again, if you feel like doing this yourself, by all means, it kind of sucks. I'm sorry, plus minus. Let's make it interesting. Okay. Now, the first two terms will be the same. Intrinsic spin squared is automatically 3/4 h bar squared no matter what. Okay. Now let's see here. What we got? Plus minus. Okay.
minus h bar over 2 plus h bar over 2. So I'm going to get a minus h bar squared over 4 on this one. Okay. And I can let me just go ahead and tell you that I know that that's it. I got myself here. Now what happens here? Okay. Now I went ahead and closed this off because I happen to know the answer. But okay. Plus minus. Okay, dead. S2 is operating on a minus state, so that's a lowering operator on the minus state, so that's 0. So this one doesn't do anything. Okay, okay, hold on. That makes that minus a plus. So they're thinking h bar, right? H bar squared. And let's see, what's the final state? Okay, that plus becomes a, that minus becomes a plus, and that plus becomes a minus. And the matrix is no longer diagonal, right? This is the whole problem. So you see that when you tried to ask the spin, the total spin of the plus minus state, which by the way would be, if this first, that would be this. What's the spin of that? I don't know. It can't be known, even though I can draw this. I mean, it looks like 0. Isn't it 0? The answer is it's unknown, which is crazy. But I'm looking at that right there. It's unknown. Anyway, sorry, I turned into a horse. Okay, so this ends up being, let's see, h bar squared, almost an eigenstate, plus h bar squared minus plus. Okay. All right, anyway, I just wanted to do 2 matrix elements just so, you know, you weren't completely lost where this stuff comes from. Okay, so now let me draw the matrix representation. And again, you know, I kind of like doing this because I'm a little afraid you folks may have forgotten about how to do this. Remember that the, what is this, the row are kets. When you have to, you know, do these elements. And the columns are bras. Let's see, that's plus plus. Minus plus. You have to turn it anyway. Plus minus, then minus minus. Okay, then I've got 4 elements. Okay, now we did plus plus, that's 2. So the h bar, 2 h bar squared. So h bar squared. Who cares? 2. And of course, since if I put a plus minus minus plus or minus minus bra on that, I'm going to get 0. Okay, so that guy is diagonal. So we have a partial block diagonal. Okay, we did plus minus. So plus minus plus minus. So that's going to be 1. But note that it also has a minus plus representation. So that means there's going to be a 1 there. And then you work the others, and it's 1, 1. Again, there's actually, you can see that this is the reason I didn't have you do this on the homework, is because it's actually kind of hideous. I'll put little matrix brackets on it. There you go. 2, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 2. Okay, so that is the spin squared matrix. Then what you do is, I actually literally, why don't you try this? Create this in MATLAB and then type. Then look up the eigenvalues and eigenfunctions, which you saw a little bit of how to do that on the finite difference module. Give me a minute to wipe out the board. Okay, I'm back. Just wiped out the board. Okay. So the eigenvalues are 0 and 2. Don't forget h bar squared. When you factor it out, you can just take the eigenvalues from MATLAB and just multiply that by h bar squared. Who cares? 0 and 2. Okay. If s squared equals 0, I asked MATLAB what the eigenstates are, and it said this. And s squared equals plus, minus minus, and 1 over the square root of 2, plus minus, plus 1 over the square root of 2, minus plus. There you go. Okay, now let's represent these in terms of the J, M sub J state, which remember is actually, you just leave out the fact that you happen to know S1 and S2. The book constantly just calls it JMJ, but you have to know 4 things. If you started out with 4 pieces of information, S1, S1Z, S2, S2Z, yeah, you still have to have 4 pieces of information. That's basic information theory. All right, but now I want to put this, now let me give it the right label. Okay, so the S is 0, and here the MJ. Now the M sub J value, you actually have to work that like you would like a P state, like, you know, plus 1, 0, minus 1. You just have to, you can just figure out what it should be without having to do any more work. Like an S state, there are no M sub, you know, for P states there's a plus 1, 0, and minus 1, but that doesn't exist for an S state. So clearly that's just 0, 0 in the new basis, in this S squared basis. Okay, now this guy, okay, now J is going to be S1 plus S2. And I know what S squared is. Okay, so hold on a second. Let's see. S squared is 2, and that is S times S plus 1, which is S squared plus S. I'm drawing myself S equal to 2. So therefore, S is equal to 1. Right? 1 squared plus 1 is 2. You have to do a little work on these. Okay. So this is 1. And of course, I can see that this is plus plus. So I'm going to figure that that's actually the 1 state. Now, I'll show you, this is an easy example to know what the M sub J values are. You don't have to think about it. When we do a hardware example, which we're going to do like right now, or in 2 minutes, it's not so straightforward, but there's a algorithm to do it. You just, like right now I'm not using it because I don't need to, but you'll see that in a minute. Anyway. Okay. Now, this one isn't hard. S is still 1. Obviously, that's the minus 1 state. Minus a half, minus a half. And that makes this, of course, 1, 0. Oh, sorry, everyone. I made a series of mistakes. I just cut out one of the benefits of doing video. I just cut out all the mistakes. Sorry about that. Okay, so last thing I just wanted to point out was that one of the reasons to do all this is that you should know that a triplet state is generally lower in energy than a singlet state. And it's not hard to know that plus plus and minus minus are triplets because we taught you that in freshman chemistry. But what's kind of interesting is that a singlet state is, you know, we think of this as like 2 electrons in the same orbital that spin up, spin down. They have to be because of the Pauli principle. That's easy. But what about this case of an electron in a 1s and another one in the 2s orbital? Well, in that case, so there's an electron in an s, in a 2s, and there's an electron in a 1s. And the singlet state in that case, sorry, it's actually minus. See how I messed it up? Minus that configuration. Whereas the triplet, which is lower in energy, ends up being like this. Go figure. Now, it's hard to visualize this. I really just don't get it. I mean, I get, so there's one singlet, by the way, and that's one reason we call it a singlet. You know, when it comes to up, up, and down, down, man, I get that. That's not hard to visualize. But this guy, up, down, plus down, up, what the hell? I mean, now I can say this, the only thing I can say to make this make any sense is why there's 3 of them. Again, up and down is easy, but this one, now we've had enough of angular momentum, right? So this is a triplet with an S of 1, a total S of 1, which basically is like a P state, right? And we know that there's a projection up, there's a projection down, and then there's a projection in the XY plane. That's what this one is. You ever notice that? The triplet is behaving just like a p state, with a p, m sub l of 1, m sub l of 0, and m sub l of minus 1. So this is the kind of behavior that you got to get used to when it comes to coupling momentum. For one, you have to do it because that's how you get the energy. And you should know that triplets are lower in energy than singlets. It's like a paradigm, especially for organic chemistry. But you can see that things that are spin 1/2, which are just spin 1/2, because of the way they add together, can form something that looks more like a p state, right? Because a p state has an L of 1, has an angular momentum of 1. And two spins that have these configurations have an L of 1. And just like there's a px, py, and pz, I have three spin states. Sx, sy, sc. That's not right. But anyway, so you see that kind of behavior. So just look out for that. Okay, last bit is to connect to your book. And this is kind of important. This is what every PhD physical chemist should know how this works. Now, recall that I just diagonalized the Hamiltonian. I diagonalized S squared. And S squared is usually in the Hamiltonian. To do that effort for every problem is a pain in the rear. Guess what? It never really matters what type of angular momentum I'm talking about. Notice that I told you these are just identical to a p state. Well, right. So the thing is that these matrices, sorry you can't see that, these matrices are basically identical no matter what type of angular momentum we're adding together. All you need to know is whether it's 1/2 or 1/2 for like spin up, spin down, or 1 for like a p state, or 2 for like a d state. That's all you need to know. And once you do that, your matrices, no matter what your problem is, will be identical. So the way that this works is, again, I see these in talks all the time. This is kind of important. So what we're doing here, remember that question mark I had before? Here's what we're going to do. We're going to take this state and resolve an identity in the M1, M2 basis set. This stuff that we just talked about for a while. And that means that we're going to form a representation that is a linear combination of these states with some weighting factors M. Okay. Right, so we just resolve an identity. And again, this is what we want because it tells us the energy, but this is what we can intuitively draw based on our knowledge of freshman chemistry. And these things are CLE, Clebsch-Gordan coefficients. Not Gordon, Gordan. It's a little weird. Okay, those are the Clebsch-Gordan coefficients. 1/2 minus 1/2. 1/2 plus 1/2. Those are the Clebsch-Gordan coefficients. So, to do this transformation I just spent a bloody long time on, I could have actually just looked up a Clebsch-Gordan table. And the table has what is this? The rows are these guys, and the columns are these guys, and then the matrix elements are plus square root of 2 minus 1 over square root of 2, yada, yada, yada. So you have to learn how to read the table, which guess what? Now we're going to learn how to read the table. That's our next goal. How much time have I got? I got 20 minutes left. Okay. So what are we going to do next? I'm going to do 2 examples. Maybe I'll do 1 example today, and then we're going to do a really hard example on Friday. Let us go ahead and do a p state. So we're going to go ahead and we have to move up a notch here because there's actually nothing more you can do with spin. This is literally it. You can never add angular momentum of more than 2 things at once. So if you have like 3 electrons like your final exam, nitrogen has 3 p electrons, and you have to figure out what all the term symbols are. You actually have to be careful because you can only add 2 things together at once. So that's, it won't be terribly hard. I'm going to show you an algorithm to do it. You just have to apply it. It's not easy. It's pretty long and complicated, but it's an algorithm nonetheless. Once you learn the algorithm, you can always do it. Okay, so what am I trying to do? Okay, so remember that the end goal is term symbols, and those look like 2s plus 1 L to the j. Okay, and we need to know what j is. So what are we going to do? So instead of adding 2 spins to get singles and triplets, which is, there's literally nothing else you can do with that, I'm now going to do a 2p1 hydrogen atom. So now we're going to figure out how to add the angular momentum from the fact that it's in a p orbital to the angular momentum of spin, up, down. To create, we're going to add those together to figure out what the total L is, and yeah, then we're going to get the term symbol. It's 2s plus 1. Okay, so I'm going to do this in an unnecessarily complicated way at first, and then we'll learn how to read a Clebsch-Gordon table. Okay. So what I want to do is I want to come up with some configurations. Okay, 1, 2, 3. Let's do the m sub L. That will be plus 1, 0, minus 1. Okay. So let's do spin up, spin up, spin up. Okay. So let's see. And I have spin down, but whatever. Those should be, you know, spin up. I can just draw the same thing and spin down, but why would I bother? Okay, now let's see. What can I figure out? Okay, I can figure out that S is 1/2. S is a half because there's only 1 electron. I don't have to add the. If I had 2 electrons, I would actually have to start adding their S angular momentum first, just like we just did. I'd actually have to do that first. In this case, I don't, because there's only 1 electron, right? But now, of course, now I have the complication of doing L. Anyway, so S is a half, no matter what. So that means that I know that whatever L and J are, that it's 2. It's a radical. It's a doublet. You ever heard of radicals called doublets? Singlet, triplet, doublets. You don't hear about doublets often because radicals are very unstable. It's very rare to find a molecule that's a radical and stable. It will react with itself at the bare minimum. Okay. So so anyway, actually, okay, I've done that, but you know what? I'm kind of messing up here. Let me show you the algorithm. What I'm going to do is tabulate m sub S and m sub L. Okay, so m sub S is always 1/2. You want to do that for when you have more than 1 electron, right? So again, I mentioned that this is actually trivial, but I want you to do it because we have more than 1 electron. It's a little bit more painful. Okay, the m sub L, 1, 0, and minus 1, technically. Okay, so now it turns out that I can see that there's no reason to think that I am anything other than a p state. Now again, this is actually kind of easy because one of the things that you have to be able to identify, you have to have some clue what the possible term symbols are. That sucks to say. It's not hard, but you have to have some intuition about what the answer's got to be because of the way you look for these. Okay, so what I see here is that my highest m sub L is 1. Now that says to me that this is going to be a p state, because p states can have an m sub L of 1. Now an example I gave, I think, yesterday, I talked about what happened if you had 2 electrons here.
that opens up the possibility of a D state. In fact, there is a D state, because that M sub L would be 2. And a P state cannot have an M sub L of 2. Only a D state can have an M sub L of 2. D, which has L of 2, has M sub L 2, 1, 0, minus 1, 2. So if I had 2 electrons here, M sub L on that state would be 2. And now I know that one of my possible term symbols is actually a D. Now in this case, it's a P. It has to be a P. So what I have to have, therefore, is, again, I've already worked out S. L has to be P. Now the next thing to do is figure out how many states are there. Okay, so the number of states is going to be equal to the number of states for each type of angular momentum. So that's 2s plus 1 times 2l plus 1, because we're adding s and l. Okay, now s is a half. That's 2 times what? Now again, I know that p is an L of 1, 2 times 3, and that's 6. Okay. Now, here's the thing, and I did this on purpose, I want to let you know, seriously, I did it. I actually played a trick on you. There's a problem. I'm looking for 6 states using this basis. I've only drawn 3 states in that basis. I've made a mistake, there has to be 6. If I'm going to end with 6 states, I have to have the starting point of 6 states. I have to make linear combinations of 6 states to get 6 states. That you have to do it that way. Now, remember before, I was talking about not including the spin downs, because like, oh, that doesn't matter. I was kind of snickering to myself because it does matter. You do need to include them. There we go. And let's go further. Okay, now the M sub s, minus a half. M sub s is now minus a half. And L is 1, 0, minus 1. Okay. Now, what we do is 2p, and I know that there's 6. Now I've got 6. Now I need to get the j. Now, it turns out, what is j? Okay, now in this type of coupling scheme, so this is called the Russell-Saunders. I hope I'm getting that right. J is L plus S, that to L minus S. Absolute value of L minus S. Okay, now let's see what we got here. L of the P state is 1, and S is 1/2. 1 minus 1/2. Absolute value. Not that you know, that's 3 halves and 1/2. Okay. So therefore, I have 2 possible term symbols: 2p 3 halves and 2p 1/2. Now, based on the spin orbit Hamiltonian, which is basically a bunch of constants, L dot S, well, L dot S is actually going to be J squared minus L squared minus S squared. I think I actually did this earlier when I was doing S1 plus S2 squared. And there's a coupling term, S1 dot S2, if you recall that. If I just did that same thing with L, you would have found that L dot S is equal to this. Okay, so this is a constant. Again, it's traditionally called A. J times J plus 1. Sorry, maybe I should be using capital. L times L plus 1 times S times S plus 1. Okay, it's not hard to see that clearly the lowest j, both these terms have the same L of 1. They have the same S. S of half. Did I say S times L plus 1? S times S plus 1. Okay. Both these have the same 2S plus 1. They have the same L, so these are the same.
So clearly the lowest J state, spin orbit coupling makes this guy the lowest energy J state. Okay. Now, last but not least, I want to point out that, so I hope I know this was kind of a lot to follow. Isn't that crazy? This is a p state with 3 orbitals and 1 electron, right? How hard is that? Well, it's this hard. It's a little sucky. It's not that bad, but a little sucky. Main thing is, write all the configurations. Surprisingly large number, aren't there? 6. I think there'd only be 3, but there's 6. We then figured out, we had to use a little intuition to figure out that we had, so it wasn't hard to get S. Now that was stupid easy. S is a half, right? Because there's only 1 electron. You don't have to be adding angular momentum of electrons because there's only 1. So S is a half, 2S plus 1 is 2, it's a double. We used our intuition to get P. Because we see that our maximum M sub L is 1, and that means that we have to have a P state. Okay, then we use the Russell-Saunders coupling scheme to figure out that there's 2 J's, a 3 halves, and 1 half. That was the flow. Now the last bit I want to point out to you is that there's 6 states here, so there better be 6 states here as well. Now how does that work? Okay, now as I mentioned, that this is J, and that there's some M sub J values. And you don't have to do any more work to figure out what those are. Just like a P state has a P of +1, M sub L of +1, 0, and -1. Let's see, I've got a P state of 3 halves, then I've got a 3 halves, 3 halves. Okay, this is the M sub J state. Then I've got a 2P of 3 halves, subtract 1, 1 half. So just like a P state, when I go take the L and subtracts 1, from L to minus, from plus L to minus L to get the M sub L's. God, sorry it's taking me so long. Plus L, subtract 1 again. Minus 1 half. And then okay. So again, this guy actually has 4 states available to it. 3 halves, and then, so that's the J, and the M sub J are just J, J minus 1, J minus 2 to minus J. Okay, 3 halves, 1 half, minus 3 halves. So there's actually 4 of these guys. Now, the 2P 1 half has, of course, an M sub J of plus a half and a M sub J of minus 1 half. Okay, so anyway. All right, so 6 configurations, 6 term symbols, and of course these 2 are the lowest energy configurations that we have. So I hope that wasn't too painful. What we're going to now do is we're going to do a 2p2. So I'm going to add an electron to this. Oh, that's going to suck. Oh, that is going to suck. You're going to really hate it when you do 3 electrons on your final. It's not that bad. There's actually, so as you can clue in, if I'm going to add an electron, I'm actually going to have 15 states. We're also going to start worrying about how to add these together using, notice I haven't used a Clutch-Gordon coefficient. I think we'll do that next time. I don't know what time it is. And in terms of going through this rigmarole, there's actually a little pictorial. It's like a Dirac. It's like Dirac notation. There's like a pictorial way to figure out your L's from your D's and P's and S's. There's a pictorial way to do it. Now here, I just wanted to show you that you can use your intuition to do this, but there is a pictorial way to do it, which still requires a little bit of intuition. It's not bad, But when we have two electrons, by the way, we're going to have three different L states. We're going to have D, P, and S. This pictorial method helps you find those really, really quick. And that's what you're going to do on your exam. So it's actually really not that bad. And then what we're going to do is we're going to actually use Clebsch-Gordan coefficients to figure out what the proper linear combinations of these guys are, to know what the actual wave functions are, because that's kind of like what we're here for. So with that, I think I'm going to sign off. I don't know if I'm signing off early because I've lost track of time. But next time, we are going to use our Clebsch-Gordan coefficients to do all that. And that will be the end of the class. And then you will, next lecture, you'll be able to answer the last question on your file. So I will see you all then.